In this example, we're going to take a look at one of the simplest possible cases, and that is how do you pump the water out of a rectangular swimming pool? So essentially we just have a swimming pool. Let me draw it like this. So let's say we have some sort of swimming pool. So we have width and length, and then it has a depth. So the depth of the swimming pool is h. So we have water in this rectangular swimming pool, and we want to pump all of the water to the ground level. Now the density of water is 1,000 kilograms per cubic meter, and acceleration due to gravity is 9.8 meters per second squared. So those are the numbers that we'll be using. And we just want to take all of the water and pump it to the ground level. So the idea is that each horizontal slice will be traveling a different distance. So the first thing we need to do is define our variable. And so what I'm going to do is I'm going to define the x-axis so that 0 is at the surface and then x goes down like this. So x is basically the depth below the surface of the water. So when we have some sort of rectangular slice like that, this will be at position x, and then it has a small thickness, which is the delta x. So when we look at the cross-sectional area of our slice, it's very simple. A of x is just equal to W times L. Since it's a rectangular pool, the cross-sectional area is constant with respect to the depth. Now, for different problems, this will not be the case. This is what makes this the simplest case, because the cross-sectional area is just constant, irrespective of depth, so we just get a constant area. For other problems, you have a non-constant area, and you'll have to figure out the area as a function of your depth, the same way that we did when we looked at volume problems, and we were looking at setting up and doing slices of volumes, and we had to figure out the area as a function of the depth. So the little volume of the slice, delta V, is WL times the delta X, because we have a little delta X here, which gives it a little bit of thickness, and that gives us the volume. So the mass, the change of mass in just pumping the ith slice to the top, is going to be the density times the volume. So it's rho WL delta X. And then the weight, we'll call that G delta M, is just rho G WL delta X. Right? If we multiply mass by G, we get weight. So this is basically the force. And then to find work, so the small amount of work in just taking that whole constant slice of water and moving it to the top is the weight or the force so the total weight of that slice times the distance. Now the variables are set up so the distance is just equal to x. So it's rho G WL X delta X. So this is the little change of work. So the total work is going to be approximately a sum over each of our slices of rho G WL X delta X. And of course, when we take the limit as the number of slices goes to infinity, this turns into a definite integral and it becomes exact. So the exact amount of work is the integral from 0 to h. So x starts at 0 and stops at h of rho G WL X dx. Now rho G, W, and L are all constants, so this is the same as rho G WL integral 0 to h of x dx, which is rho G WL h squared over 2. So the total work in pumping all of the water in the rectangular swimming pool to the top is just rho G WL h squared over 2. Now, WLH is the total volume. So let's take a look at this. This also has an interesting interpretation. So WLH is the total volume of water in the tank, because we just have W times L times H. So WLH is the total amount of water. Rho times WLH is the total mass of water. So this is equivalent to mgh over 2. Total mass times gravity, so the total weight of water, times h over 2. Now h over 2 is the distance that the center of mass of the water in the pool has moved. So we have this interesting observation that this formula is actually equal to just the total of weight times the distance moved by the center of mass. And so perhaps that shouldn't be too surprising, but it's always nice when we get a result that kind of makes sense with physical intuition. Why would it be anything else?